Thank you, Christine. So today's session, we will highlight just 4 of the many researchers at App State that conduct sensor-enabled research. Speakers will give a brief overview of their research and describe their instrumentation and data collected, and what related and persistent challenges they face. Because we know of many more working in this space, we're offering to host a follow-on research roll call on this topic. We'll share the link to that poll. If you're interested in joining that, please complete it. And remember that our sessions are recorded. I actually was a little late in starting the recording for this one. I accidentally stopped it when I meant to restart it. But the recordings are trimmed and uploaded, processed, and put on our YouTube channel. So those, we'll share that link to our YouTube channel too. You can see some past events and recordings there. And we'll also share a link to a form, I think Christine's grabbing that now, that will help us follow up effectively and offer programming that continues to add value to the research enterprise here at App. So for today, we have 4 speakers. They are Bill Anderson, Jeremy Ferrell, James Sherman, and Shea Tuberty. And I'll go ahead and just introduce them all, and then they'll go in that order. So Bill Anderson is a professor in Geological and Environmental Sciences and is broadly trained as a hydrogeologist and civil engineer. Bill's research uses modeling and field data collection to quantify the controls on groundwater flow and solute and heat transport dynamics in unconfined aquifers in the high country, England, Wales, and the North Carolina coast. He also prioritizes undergraduate research experiences in that. Jeremy Ferrell is assistant chair and an associate professor in sustainable technology in the built environment department here at App. His research focuses on renewable energy innovations that serve rural under-resourced populations, particularly in smallholder agricultural applications, including controlled environment settings such as greenhouses, which I suspect is what he'll focus on today. James Sherman is a professor in physics and astronomy department. He oversees NOAA and NASA aerosol monitoring sites at App State, one of which is the longest and most comprehensive active data sets on the optical properties of aerosols. And Shea Tuberty is a professor in the biology department. He was recently named director of the university's new quality enhancement plan, focused on climate literacy, resilience, and climate justice. Shea is an ecotoxicologist and with collaborators in geography and planning, maintains an extensive monitoring network along the upper South Fork of the New River. So we'll give each speaker about 10 to 12 minutes, depending on where we are on time. We'll take a question as they transition slides. Some speakers can stay on past the hour. So if there's good discussion going, please feel free to stay on. We will stop the recording and allow that discussion to ensue. So we'll give a reminder about that at the end, but a lot of the Q&A will occur during that time because we have a packed day with 4 speakers. So without further ado, I'll turn it over to Bill. Thank you.
Great, thanks. Thanks for hosting this event. Get my screen share going. I'm going to talk about sensor-enabled research that I've done related to hydrogeology and hydrology. I've been using sensors since I was in grad school back in the early 90s. So I've seen the technology change quite a bit over the years. And so I'm just going to give you an overview of what I do. So mostly what I'm interested in is not studying a site in particular, but understanding processes. And I do a lot of that work in groundwater, riparian aquifers, so stream adjacent aquifers. I've worked in fractured bedrock hydrology. I've looked at groundwater connections to climate signals, done a lot of work in freshwater aquifers on the coast here and in the UK, looking at storm events and sea level rise effects. And I'm going to give you a particular example on stream temperature monitoring that I've done for the past, well, I guess really just shortly after I got here in 2004. So the kind of sensors I use are pressure transducers. I have 4 stream gauges. I think we just decommissioned one, so we're down to 3 stream gauges that use telemetry. These have gotten easier and easier to telemetrize over the years, and I think we've had telemetry on these for about 10 years. Mostly we use these to measure stream stage, and then we have developed rating curves, which are a necessity for studying and developing stream discharge. As with all these, the potential problems are vandalism, loss of telemetry, and we've noticed in these types of sensors, instrument drift. Also use similar pressure transducers in coastal settings. Again, vandalism at some of these sites, animal damage. If you have any sort of wire sticking out, even if you've buried it underground, animals seem to find those and chew them up. So that's been a problem. In coastal North Carolina, we've had people shoot them up for target practice. So that's a problem. We also, over the years, have used electrical conductivity sensors. Mostly this is to measure electrical conductivity and convert that to salinity. We use that to monitor road salt in the high country and to study coastal aquifers at my sites. This is one in England that I've done a lot of work on. These are subject to storm damage. Sometimes this beach completely disappears after a large storm event. Theft and vandalism, although we had this site right on the Southwest Coast Path for 2 years and no one touched it. So that was nice. And then temperature sensors we use a lot. We've started putting these into Boone Creek and some tributaries back in 2006. The main problem here is just how dynamic the stream is. We've lost some sensors because of storm events over the years. And occasionally when there's a stream cleanup, somebody will pull one out. I guess because it looks like it's trash. So what I do with these data is I combine them with techniques that I use to understand the site in particular. We use geophysics, sometimes field mapping, but we combine these data with some sort of modeling. In essence, I mostly do modeling to understand systems. They can be analytical or numerical models, regional models. Sometimes we do tracer tests and we model those data. And also we do some time series analysis. So this would be an example of a modeling output that one of my students put together, but this is road salt adjacent to Boone Creek, modeled over the course of the summer where it remains, starts to arrive back in winter. And you can see here by April, we have salinity all throughout the riparian aquifer, and it's still there the following July. So we use that to understand how long materials stay in the ground. So in terms of the data that I use, like in terms of tracer data, this isn't a site or an application where I will just put a sensor into a well, say, and just let it sit there. In this case, we actively do a test in the well. And in these tests, this was back for my master's thesis, we replaced the saline contaminated water with fresh water and then started pumping that well. And we looked for the return of salt to the aquifer. And these were discrete fractures. And we were able to estimate the permeability of those fractures just by modeling these changes in salinity in the borehole with time. So that's one application that I'm using environmental sensors, but I'm not really measuring a time series. We can measure a time series, though, and apply more regional models and using those data then as a calibration model. And I did this with a student back in 2008, where we modeled hurricane overwash, and we allowed those data that we collected to serve as our model calibration tool. And you can see we match up pretty well. The blue line is the model, and the red line is the measured. Up here, it's measured salinity, basically, and down here is measured water level. We don't have any water level data in here because the sensors were completely destroyed by a hurricane. And then finally, we look at temperature data. And these temperature data are really fairly easy to collect, except for the occasional storm that knocks them out. Sometimes we collect water levels and we do the hydrographs and so forth, and develop stream hydrographs. A lot of what I do is collect temperature and salinity data. The salinity data are really important to drive our models. They actually give us boundary conditions for our models. And stream temperature I've been using lately to look at urbanization effects on stream temperatures. So this is a data set that I've used recently. The site contains, or these data here contain 120 site years of stream temperature data. Like I said earlier, we started back in 2006 collecting these data, and the pandemic kind of shut down our efforts in 2020, and we really haven't gotten back to it. But I'm going to do a couple minutes here just about what we do with those data. So if we take those time series that I just showed, we can think of those time series as an annual oscillation and then a daily fluctuation in those data. So what we do is we take those data, these are daily average temperatures, and we figure out what the annual fluctuation is just by fitting an annual curve to that using this equation. So we can figure out what the mean annual temperature is from this data set that we collected, and then we can model the best amplitude that gives us the best fit to those year-long data. If we then take those data, that curve of best fit, and subtract the real data from that curve on each day of our data set, we get a residual data. And those residuals can be modeled by looking at three things. We can look on the memory of the system. How important was yesterday's temperature to today's temperature? How important was 2 days ago's temperature to today's temperature? Those are dictated by the data series that we've collected. But then we can also look at the air temperature at a site and try to get the best fit to our data by choosing some sort of thermal exchange coefficient. So what this looks like in a data set, if we combine all those factors together, this is data from 2015. And we've divided this Boone Creek into an upper section up at the upper end of downtown, a midsection around mid-campus, and then the lower section, we stop our monitoring down at Durham Park. And the R-squared values for the fit to these data is about 0.98, which is a good value. And what those data tell us is, how does the stream behave in terms of those environmental parameters I was talking about? And it tells us a little bit about the urbanization and some factors like that that are affecting how those temperatures respond. So we've learned quite a bit of interesting information about urbanization effects on stream temperatures just by taking those measured data that we've collected with environmental sensors and utilizing those. So I think I'll stop there, and I'm happy to answer any questions that people may have at the end of the talk or now if we have time.
Thank you, Bill. That's really interesting. And we do, while we're transitioning slides, we do have a little bit of time. If anyone has a question, you're welcome to put it in the chat or just unmute and ask. And Jeremy, if you don't mind queuing your slides up. Well, Bill, I'm curious if you have sensors in other locations beyond, I may have missed it in your slides, but beyond Boone Creek. Sorry, you're muted.
Sorry about that. Yeah, we have a sensor. We have a stream gauge out at the Greenway. We have a whole well field out there that we occasionally monitor water levels out there. In terms of stream temperature, we just decided just to stick with Boone Creek and try to understand. When we got the initial funding from the provost back in the mid-2000s, the goal of that research was to understand AP's impact on the environmental health of Boone Creek. So that's what we focused on.
I see. Thank you. And Christine, you had a question?
Yeah, I was just curious. This may be a more in-depth discussion we could do at the end, but I was wondering if you and this work have looked at any correlations with other urbanization metrics that might be out of, like, land use or urban planning groups. Would there?
Yeah,
relations?
we have looked at different parameters that affect that. Yeah, I could go into more detail with you. I gave a talk in the department at the beginning of the year where we looked at some of the more obvious impacts that could be affecting these temperatures. So yeah, we've gone into a lot more detail.
Thank you. Okay, Jeremy, could we go ahead and get started with yours if you're ready?
Okay. Okay, how's that? Can you see that?
There are some gray boxes on my view, but I do see the slide.
Okay, I think I just moved the control panel. All right, thanks everybody. My name is Jeremy Ferrell. I am an associate professor in the Department of Sustainable Technology and the Built Environment. And I just wanted to take a little time to talk about a relatively new effort within the past 5 years, but it's really launched me into sensor-enabled research, mainly in the controlled environment agriculture space. I'm going to be talking to you, as Grace predicted, about greenhouses. And so this project, we call it the Nexus Project. It's a name that we've used for a while, and it's really the intersection of energy and agriculture and the role of sustainable technology to enhance farm productivity. This is really largely part of a group of faculty in sustainable tech and the built environment that have a bio and ag engineering background like myself, or a civil engineering that's turned into more of an environmentalist, or a chemical engineer that's turned into more of a general researcher. And we've combined to form this group where we're really looking at a few different technologies, greenhouse efficiency and automation. I'll talk about that. Root zone heating, ways to heat a greenhouse more efficiently, season extension and supplemental lighting is really in the greenhouse domain. And then there's also an effort as part of this group about organic waste management, looking at nutrient cycling with anaerobic digestion, biochar, and composting. And this is part of an ongoing project that's brought in external funding from EPA, the North Carolina Department of Ag, and the USDA. And so I'm going to talk a little bit about our greenhouse. Okay, so the main sensor work that I'm currently involved with is for greenhouse monitoring. We're mainly looking at environmental sensors and electrical data. We're looking at energy use in greenhouses. And so it's pretty much electrical and propane. And so we're looking at propane. I don't have a sophisticated way other than figuring out when Suburban comes and fills tanks, but electrical, we do have transducers. We have CTs on all the circuits of interest. And these are my my main collaborators that I'm working on, Hey Young Kim and Okyun Yu on the Nexus facility and Springhouse Farm. And then out at Blackburn Farm, or what most people refer to as the SD Farm, the SD department manages the Blackburn Farm, the agricultural part of that. Chip Hope is the farm director out there, and then Andrew and Wyndham and Brian Reichel goes in my department. And so really looking at greenhouses, how they perform, we're seeing a really pronounced trend in the production of food under glass and plastic. There's a real significant movement. It's about a 10% annual growth in the greenhouse market worldwide due to erratic temperature, rainfall, so on. So more control, this seems to be the route that we're going. And greenhouses can be a good solution. Certainly a lot of factors, but we're interested in looking at the impact from the energy use associated. So our data points are generally environmental. We do these in 5-minute frequencies: temp, relative humidity, pressure, solar radiation, photosynthetic active radiation of FAR, wind speed and direction, rain gauge. We look at soil depth. We have these meter-long probes that we look at moisture and temperature. And then we, as I mentioned, we look at electrical usage. So there's a picture in the top right of graduate students wiring up sensors in series so we can put them on underground one of these greenhouses, look at temperature. There's Brian Reichel, some of you all know him. He's helped with putting the CTs in. And we have these primarily on what I thought at the time was the cheapest and best research grade option, which I still generally think so. We use a lot of things from Onset and the HoboLink for organizing our data. So we have a HoboLink. This is a little screen capture from the 4 different locations. We have the Atlas and Ceres greenhouse at the SD farm, our Nexus facility. And then Springhouse Farm is one of our partner farms. We have worked with a few partner farms around the high country, and this is the one that actually has active monitoring. So this in general, I think, is a pretty good platform. They don't have the compatibility for our electrical, so we have another website that we electrical, and then we still have one data set that is local. We have to go out there and download it from the greenhouse itself, and I'll talk a little bit more about this in a minute. It's the ground to air heat transfer. We're looking at the soil underneath the greenhouse as a way to store heat. So the platform, the HoboLink platform, is pretty good. There's a public access, and then there's a more enabled login that we use to download data and do analysis. So I'll give you a little example here. This is the greenhouse project under construction out at the farm, ASU Farm and Blackburn Farm, and it was a really great opportunity. It was during the height of our pandemic experience, but we were able to get a special permission and work with students to go out and construct this big heat exchanger, which is a series of pretty commonly sourced drainage pipe, 4-inch corrugated drain pipe and small culvert pipe that we could get locally, and build this heat exchanger that allows air, the heat transfer fluid, to exchange heat from the greenhouse to the ground, or from the ground to the greenhouse, depending on the conditions. And it's located right next to the high tunnel traditional poly-covered greenhouse here. So we have a setup, a longitudinal study to look at those two. This more pictures from that. You can kind of appreciate all of these tubes have pole wire in them. So that the picture a couple slides ago with the grad students wiring up sensors, those are actually in these pipes underground. So we're looking at temperature across the heat exchanger underground. And this is the drawing. We worked with a company called Ceres Greenhouse Solutions, thanks to one of our graduates that got a job there. And I'll show you a little bit of data from this here. So some of the sensor enabled work is allowing us to look at things like efficiency, how this ground air heat transfer works, how effective it is. It works kind of like an HVAC system or a heat pump. It can cool and it can heat, and it can do that within 24 hours. So we have a cooling mode here and a heating mode here, where depending on the inlet and outlet temperatures that we're looking at, and quantifying the coefficient of performance. So how effective is this essentially at moving heat, kind of like a heat pump might be in the 2 to 3 coefficient of performance. We're seeing similar of this GAT system. So we're looking at this as an example using the data that we're collecting. Another example here is looking at photosynthetic active radiation. It depends on the glazing material, if it's polycarbonate, if it's 1, 2, or 3 layers of polycarbonate, or if it's sheet plastic, or if it's glass. And so we're looking at some of the differences in selective glazing in these two. In this slide on the left, the slide on the right is looking at solar radiation. And so really, I've been able to use this in class. I teach a solar thermal energy class, which has been great. We've got this live data stream that students can do assignments with directly. We also have had 2 master's theses use data from these sensors. One did an analysis of the ground air heat transfer system. Another looked at the data from the Nexus facility. We automated the ventilation with these side walls that roll up. And she looked at the efficiency gains from that. On the challenges side, we have a hotspot at Springhouse Farm. We have had wireless base stations. We've had wired stations. So far, I found the wired onset stations are the most reliable. But we've experimented with all three of those things. We have kind of like Bill mentioned, we've seen the sensors have some reliability with calibration and drift over time. Soiling is an issue. A lot of our stations are kind of like an outdoor weather station, so they can be, covered with dirt or soil, or or even snow occasionally, and wondering why you're not getting any solar radiation. Well, it's because it's covered. The sensors seem to be expendable in nature. There's no real way to replace them or warranty them. They're $250 for a temp, relative humidity, wireless sensor, and if something goes wrong with it, it's pretty much expendable and done, and you just have to replace it. So that leads to the ongoing replacement costs that seem to come up with this. And finally, organization and management is something that I'm working toward. We do have these 3 different platforms, so getting things in an organized place where we can build a research program is a challenge. Matt, fortunately, who I think is on the call, is helping me organize this better. Yeah, I think that's it. A little short, maybe a little under time. So if there's any questions, I'd be happy to go into anything if anybody has any further comments or questions.
Thank you, Jeremy. And we do have a couple minutes here for questions. Well, if you want to start, maybe stop share and we'll let James go ahead and get his slides queued up. Thank you, Jeremy.
You're welcome.
I could ask one question, because I know how much of a labor of love that whole smart greenhouse building process was. Do you have, if somebody said, what was the most surprisingly hard thing about that process? Was there a challenge that was just stands out as being more difficult than you anticipated regarding the sensors and the data?
Yeah, I mean, part of it was we didn't have internet at that greenhouse. There was an air mesh system that had been put together, but it was very unreliable, and so it took quite a while to figure out that our wireless base station was only getting sporadic connectivity due to the internet. At one point, it got unplugged. At one point, it got cut and disconnected. So there was just a lot of things that are not really part of my training that I had to figure out or ask the right people to help with. But we do have fiber out there now, and as soon as we installed it, we've had other people jump on with research. So the B project is out there, Raman's project is out there now, and so I feel good about that. Paving the way for some infrastructure for other folks to use as well.
I have a quick question for Jeremy, if that is fine. Yeah. So Jeremy, I'm Bhuvan. I'm from geography. I'm a new faculty here. I work with wind and crop loss. So do you have any experience with wind monitoring and agricultural field here?
I don't personally have experience with that. We are collecting wind data, but more to look at heat loss from the greenhouse. That's primarily what we're looking at. There is a wind expert in our department that I could connect you with. His name is Ram Podal, and he could be a good contact for you. I'd be happy to send you his email.
Okay, good. Okay, great. I know him. Okay, thank you so much, James. Yeah.
Great, thank you. Okay, James, if you want to go ahead and get started.
All right, so I'm going to talk a little bit about some of the aerosol research at Appalachian, and I'm going to focus on the instrumentation, but just a couple minutes at the beginning to basically take our heads out of the forest and see why we're doing this. So here's a picture of Great Smoky National Park, and To the left is a typical summer day in the early 90s, and to the right is 2011. And you see that the haze has decreased dramatically in the southeastern US in the last few decades. And a lot of that is due to the reduction in anthropogenic emissions of atmospheric aerosol precursors like SO2 from power plants and NOx from combustion. So these aerosols are really good. Well, they're good and bad. I guess they're bad for air quality, but in some respects, they have a positive aspect in that they tend to be very good at reflecting sunlight back into space, and they tend to produce a cooling effect on average, which in some regions can partially cancel the warming effects due to greenhouse gases. Here's what aerosols are, and here's their effects. So we observe them as dust and haze and smoke, and that gives rise to the blue haze. The Blue Ridge Mountains are named after the blue haze that you see in the summer in the southeastern US. And these aerosols directly affect solar radiation budget by scattering and absorbing sunlight, primarily scattering. So that reduces the solar flux at the surface. But even more importantly, they serve as the seeds for cloud droplets to form on, and they modify cloud lifetimes, rainfall potential, and cloud reflectivity. And so these effects, here's the latest IPCC report on the uncertainties. These are global average, so they're bigger in some regions. And this is what's called radiative forcing, and it has units of watts per meter square. And don't worry right now about the units, but positive numbers like for greenhouse gases means they produce a warming effect, and the air bars are very small. And negative effects such as the purple and the gray here are due to aerosol effects from the different aerosol types. And you see that these are negative and that they have much bigger air bars. And in fact, the largest uncertainties in predictions of future climate are due to the aerosol direct effect, the gray part, which is the scattering and absorbing of sunlight. But more importantly, it's due to these aerosol cloud interactions and how aerosols modify clouds. So that gets into why we initiated these measurements up at App in 2009. And here are the main objectives of the research. The first goal is we're trying to understand better how changing air quality and climate change are related in this part of the country. They call the southeastern US warming hole, because it's one of the only a few regions that didn't warm in the 20th century. And aerosols played some role, at least in the summer lack of warming in the region. So we're studying that. The newest, I'm trying to get now into these aerosol cloud interactions, which we're starting to get into because that's like the holy grail in climate models. So we will be starting that with field campaigns in the winter and summer of 2024. They just got funded, but I'm not supposed to say anything because it's not formal. And that's between App and Georgia Tech and NOAA. And the goal is to train models to predict cloud condensation, nuclei, and aerosol liquid water, which are two of the big uncertainties. Satellite validations is another. We validate satellite-based aerosol retrievals. Everybody likes to use satellite data, but many people don't know how its limitations, when it's good and when it's not, and it's often not good. And then we started a network of handheld measurements in Africa and the US to try to fill gaps where there are no ground measurements. So here's the Appalachian 1 site. It's up next to the baseball field by the old Broyhill. And you have air coming in from this 34-meter tower into this. It's not a building, it's a shed, I guess. So it comes into this shed and it gets divvied up into all these different instruments. And I'll go into these for a few minutes. in event that others are interested in using the data. Each one has many sensors, so I'm not going to get into the sensors of each. But the air comes in here, and this instrument here and down here is called a aerosol scanning mobility particle sizer, which measures all of the diameters of the different particles. This is what's called an aethalometer. This right here, it measures black carbon concentrations and the spectral light absorption of aerosols. This is what's called a tapered electromechanical oscillating microbalance, which measures PM10 mass concentrations. This instrument here is called a CLAP. It measures aerosol light absorption. And you have two nephelometers here and here. The first one measures aerosol light scattering and backscattering for dry aerosols. And the second one humidifies them every hour. And from the two, you measure the hygroscopic growth of the aerosols. This is a condensation particle counter, which measures the number of particles per centimeter cubed. And we just added an instrument on loan for NOAA for our field campaigns, a cloud condensation nuclei counter to start the cloud studies. So these are what are called in situ sensors. In other words, the air is directly pulled in and sampled by the instruments. The remote sensing sites are on the library parking deck in this shed. And this is a Simul sun photometer. It's a scanning robot which wakes up every few minutes, and it scans the sky, and it measures what's called aerosol optical depth, or the column integrated light extinction from the sun to the surface. That's part of NASA's aerosol robotic network. Chris Thaxton has some weather sensors up here. I have a Kippenzonen solar, which is a WMO, World Meteorological Organization grades pyranometer, which measures direct and diffuse radiance as part of NASA Aeronet. We have an all-sky imager, which takes pictures of the sky every 5 minutes and calculates cloud fraction, or it did until the vendor quit supporting it. We have a micropulsed LiDAR as part of NASA's micropulse LiDAR network that sends a LiDAR beam up in the sky, and it gets echoes as a function of altitude and measures vertical profiles of aerosols and clouds. And we have a PM 2.5 monitor here, which measures PM 2.5 mass concentrations for air quality studies. So most of these are what are called remote sensing instruments, because they don't directly sample, but rather they use transmitted or reflected sunlight or light from the atmosphere to measure properties of the atmosphere. Each one of these also has several sensors in it. I'm not going to talk much about this, but we started some handheld measurements in Africa, North American and Sub-Saharan African Mountain Aerosol Network. We called it NASA Man when we were trying to get NASA money, because they like acronyms. And the goal here is to fill voids in some of the air quality and climate change measurements in Africa. This project's kind of on hold because I have to get some funding for it right now. So the data sets have been used by the aerosols working group of the latest IPCC climate assessment report, as well as a host of different studies about Saharan dust transport, aerosol hygroscopicity, satellite variations, aerosol precipitation, and then several different global studies. The data is uploaded to the World Meteorological Organization's Global Aerosol Watch database every year, as well as NASA and NOAA websites in near real time. Couple sample data products. This is what's called the scattering coefficient. You can think of it as proportional to the amount of light scattering aerosol in the atmosphere. And it shows that when we started in 2009, the scattering was quite a bit higher. And then it hasn't changed too much since about 2016. Most of this decrease is due to the decrease of SO2 and sulfate aerosols from coal plants. The aerosols have become much less hygroscopic. It started to tank in 2016, and that has effects on their ability to scatter light and serve as seeds for clouds, which is leading us into some of the newer studies. Here's a picture from last night. If any of you were outside and smelled smoke, this was from the LiDAR, and this is altitude, and this is time. And the cooler colors are less aerosols in clouds. Here's a cloud. Here's some aerosol in the upper atmosphere, which is smoke. Here at night, when the boundary layer starts to collapse, it comes down toward the surface, and the levels got quite a bit higher as we got toward early evening last night. Challenges and collaboration opportunities. So basically, we're running 13 instruments 24/7 without any technical help except as able the college technician with repairs. Stable budget is an issue. Interdisciplinary expertise. Appalachian started as a collaboration between 6 departments. Many faculty either left the university or found other areas of research, and so that needs to be rebuilt. What types of collaborations would be helpful? Well, somebody with modeling background, GIS is really important because we're trying to understand where these aerosols are coming from and the influence of changes in pollution and mitigation strategies on the aerosol, and air quality biosphere interactions would be helpful. So that's pretty much it.
Great, thank you, James. We are a little tight on time for this transition, so if you don't mind to stop sharing, and I'll have Shea go ahead and queue up his slides. And just a reminder for those that joined a little late, some of the speakers can stay on past the hour, so if we do run out of time, there'll be plenty of time afterward for conversation. Okay, Shea, you're muted, and if you want to share screen, there we go, perfect. Thank you, James. Okay, Shea, it's all you.
All right. All right, are you seeing my notes or not?
No notes. We just see
Perfect.
yours.
Okay.
Yeah.
All right, so I saw Jeff Colby's joined me. Derek Martin couldn't be with us today, but and Sean Uyghur's moved back to China some years ago. But this was the original team that we were calling App Aqua, along with Kristen Cockerell, an IDS, who was kind of our policy person. But what we've done is installed, like Bill Anderson has done, some real-time instruments. We didn't set up with telemetry, but we called them trolls. Most of these are it's kind of the common name for them. These instruments are usually mounted underneath a bridge. And this was a talk I gave at the New River Conservancy, I guess 3 years ago. And we just called it, you don't always get what you want, the trouble with trolls, but we talk about challenges with these things, and there's many. So kind of start off with the multiple issues, not to complain too much, because we really appreciate the university support. Going way back with Stan Eshelman's, I think, $75,000 investment to purchase some of these initial sondes. I think Bill and Chris Thaxton in physics both were messing around with these initially. And then I think a year or two, maybe 3 years later, Jeff and I started just trying to get them installed someplace so they were actually starting to collect some data. So the installations have evolved over the years. We've had a lot of help from the guys over in Garwood and manufacturing and installation that would last through some of the things I'm about to show you. But we get a lot of high flow damage due to our flashy streams. And the increased number of floods has made that even tougher. But we put them in places where we can access them at low or high levels typically. In some cases, we had to search out permits with NCDOT if we were going to mount them on one of their bridges. Other cases, we were working with local landowners. This picture I've got down here with Jeff and I, that was probably a February maintenance trip we took in a foot of snow up on Flannery Fork. This is mounted under a private bridge for one of the landowners there. So it can be kind of difficult just to get these things put in place. The probes last typically 3 to 5 years with lots of breakdown that we have to constantly keep up with. We're on our second group of data sondes now that typically have fortunately become much cheaper. So we went from about $9,000 a piece to as low as $1,500, $3,500 a piece. We have to go out monthly, change out batteries, download the data, manage the probes, calibrate everything. And it can be tough with the timing, although we've been doing this for 11 years now. We know that in the wintertime, our batteries may only last 2-3 weeks. And there may be some ice and freezing, making it impossible to even get into the installation until it thaws out. So we start off with in situ trolls. These 9500s, like I said, they were about $9,500, I think, at the time. And now we've switched over to Eureka. The trimeters are kind of a low cost sonde. And we have a Manta, which is a little better. And I'll get to what we're collecting here in just a second. But they are installed at 8 different locations in the upper South Fork New River watershed. That's the small creeks that form the South Fork here in Boone. And basically what's upstream of the covered bridge on the South Fork at the Greenway over at State Farm. These are collecting for sure temperature, conductivity, and depth. That would be like our low-cost trimeter, and then a couple of the mantas and other things can catch pH and dissolved oxygen as well. We've been monitoring every 15 minutes, capturing data at every 15 minutes at all these 8 sites, and they are installed at places intentionally to capture the range of water qualities in our subbasins from the most high quality pristine ones coming off the parkway to the most degraded that's draining a lot of impervious surface here in town. This isn't our most updated maps, but these are basically showing our 8 subbasins. What is different now is that the State Farm one has now separated Hodges Creek, which is this westerly flowing section of headwater stream coming under 105. And that's separated from the monitoring site at State Farm at the covered bridge. But it gives you an idea of where these things are found here in the county. This is a breakdown just within the county. And then we can use this data and the land cover data that Jeff and his students have been producing over the last few years to create some nice layers that we can then demonstrate how land use and cover is actually affecting things like water quality. So here you've got forested sections in green and impervious in white. And then next to it, we've got the subbasins with the median or mean conductivity, which is a measure of water electrical conductivity or specific conductivity measured in microsiemens per centimeter. And basically the lower the numbers here, the more natural they are. And so you can see we've got 3 sites that are fairly low in that 30 range, which indicates high water quality, and then a few that are in the mid-range, 50 to 100 or so, and then some of these are much higher. The one that's draining town and the university campus is well over 400 now. And you can see the number of individual data points that these represent. This number would actually be about 2 or 3 times that at this point. These are kind of old graphs. Other data that Jeff produces look like this. So now we can just basically pull out the forested and then show the impervious specifically. And then he's done some more highfalutin LiDAR capture. So this is just the middle fork section of the watershed that was, we had some LiDAR data captured from one of our students, like Jeremy's, that have gone on to great things and worked with awesome firms, and they were in the area, so they donated some data to us so we could look at some of this super high resolution land cover data. And then we can start getting into relationships between the water quality and land use change, land cover change over time. So this is another way of looking at that data. You could actually look at the forest cover and proximity to the riparian edges of streams, and we can start looking at physical aspects of the stream and what's affecting water quality as well over time. So these kinds of high-end, I don't know how to work with this. I'm leaving this to Jeff to figure out, but I'm sure there's a lot of applications that some folks in the audience might can imagine for using this data for. We only have this for the Middle Fork currently, but I think the long-term plan is that we get it for our entire watershed and start looking at time scales and differences over time as well. So as far as getting these things installed, these are what the instruments look like. And then the mounting that you see on the concrete walls there and the natural rock, these are examples of how we install these things in places that maintain protection for the instruments, easy access for us at all levels of water flow. And it's taken us quite a while to get where we're at. I think we started with 4-inch PVC, and now we're ended up with just solid aluminum pipes that have some great laser beamed out of the middles of them, so it allows water to pass through them. And we've got these, places that you might recognize, the Deerfield Bridge over by the hospital, one of the bridges just upstream of A&B Brewery. And so these have been out there for 11 years, and they've collected a lot of data. Some of the other things we've had to do is create standard operating procedures for the undergrads and grad students that help us out on a monthly basis. We've got that kind of well-designed, and we're starting to see a lot less data interruptions just due to user error and mistakes because of the check sheets that we've created have been very helpful for the students. And then some time ago, I guess it's been close to 8 or 10 years now, we did get some internal funding to support building a GUI, graphical user interface, that would use the data that we've got in our database, and then we could do searches based on time or sub-watershed and the water quality parameter you're interested in. You can create graphs very quickly. That got migrated to a new platform this year with some upgrades, so that's been really fortunate for us as well. So some of the issues that we deal with and some of the fun things you can do with these instruments is to look at some of the flooding events. We don't have time, so I'm not going to click on this link, but basically that October 23rd to 2017 event created one of the highest flows in recent memory. And some of the lasting impacts that happened once it had subsided are just lots and lots of trees and whatnot hitting our sonds. This is the one at Goshen Creek, so it's basically exposed for about 8 feet here. And after one of the more recent, it survived this event, but more recently it cleaved right down the middle, and the actual instrument got cut in half. It looked like somebody hit it with a samurai sword and just cut it cleanly. I have no idea how that could have happened. But we found the other half of the son laying in the water just downstream. We've now replaced this with an aluminum pipe. I don't think it's going to have any problems. This is the one at the Middle Fork. This is one on Flannery and Winkler's Creek, I'm sorry, on a private property. This is another one that was that we kind of wedged underneath this tree and strapped it to it, and then that flood actually removed that tree, and our installation pipe has never been seen again. So there are problems with high water events that make it almost impossible for us to keep our instruments out there. This is the place that upstream of A&B, and so the vegetation gets stripped out of that, piled up, and we've had to dig this out multiple times. Another one is installed right here by the sewer line that's crossing at just upstream of the covered bridge, and that sewer line also catches all kinds of other interesting things like dipsy dumpsters, bloated beavers and trees. So it's a constant effort to keep these things cleared of mud and debris and working for us. So that's one of the things the kids have to work on constantly when they go out to visit these things. So the kind of summing up what we've got so far is greater than 11 years of sub-basin data for 8 different sites. There's millions, I think 1.5 million data points at this point. We're starting to see very strongly negative relations between impervious surface and a number of our different water quality parameters, especially conductivity. We can see strong positive impacts from forestation up to 30 or 50 meters, negative up to 100 meters. And then we can start to separate these subbasins into 3 different categories based on their relative water quality. And so we've been using that to study things like relationships with fish and invertebrate assemblages at our different sites and our different subbasins, as is impacted by road salt, for example. And we can start to look at stream rating curves and discharge to get an idea of losses of salt, phosphorus, other things that we're working on. So if you just take a relationship between one of the metrics of aquatic insect diversity, in this case, the lower the value, the better, and plot that against some of our water connectivity at our different sites, we can start to see that there's some breaks in the data that represent the low, mid, and high levels of impervious surface or road salt application we see in our subbasins. So it's a pretty nice relationship. And Derek Martin uses some of the discharge data to create some of this hysteresis results. I'm sure I said that wrong, but he's relating it to chloride or road salt and looking at how these peaks in road salt wash off relate to the beginning or the end of some of these high water events. So I'll stop there.
Thank you, Shea. You saved me from having to try to verbally interview. We are right at the hour, and I know some people have to leave. So I was, thank you for that. And there are a couple of the speakers can stay on. I'm sharing some links in the chat here, but I'll pause for a second to thank all of our speakers, Bill, Jeremy, James, and Shea, for making some time to speak today, for everyone that joined in the audience. And this will be processed and uploaded to YouTube before too long. So you'll be able to share it on if you have some others interested. And then just another reminder that we have one more session, April 28th, focused on alternative proteins. Join us for that. And also for faculty and students here, we're hosting a listening session for the new RIEEE Student Scholar Program, which we're kind of soft launching now, but we'll kick it up or kick it off for real in the fall. But that listening session is going to be on April 21st. Watch for some announcements about that. And I will go ahead and stop the recording so we can close that. And thank you.